back to the series, and I'll be covering more about Max Planck's equation today, and I'll also be giving you an example that I covered in some of my sessions with individual learners. So, what is Max Planck's equation again? So, as I said last time, E is equal to hv is Max Planck's equation that relates energy and frequency of a wave. So I didn't tell you exactly what h is in this equation, but I will now. So h is known as Planck's constant, and it is equal to 6.626 times 10 to the power of negative 34 joules seconds. So the standard unit of energy is joules. So that's why we use joules here, and we use seconds here because it's a canceling term for the unit of frequency. And you'll understand more about how this works when we do our first problem. So here it is. What is the frequency and energy of blue light that has a wavelength of 400 nanometers? If I were you, I would pause the video right here and I would try to work it out myself. Here's a hint. It would use both E equals to hv and the equation that we talked about last time, which is that wavelength of a wave times its frequency of the same wave is equal to the speed of light, where speed of light, which is known as the constant c, is equal to 3.0 times 10 to the power of 8 meters per second. Okay, meters per second, yep. Alright, so you're still here, so let's calculate our example problem. So the first thing that we'll need to do is find out the frequency, because Max Planck's equation to calculate the energy requires frequency. So calculating the frequency is relatively simple. So let's start by plugging into this equation. So 400 nanometers times our frequency is equal to the speed of light, which is 3.0 times 10 to the power of 8 meters per second. And I would advise you to have a calculator because there is no guarantee that in chemistry problems will be easy to calculate mentally. So now that we know this, we rearrange it so that we can solve for frequency. And we say frequency is equal to 3.0 times 10 to the power of 8 meters per second, all divided by 400 nanometers. And since it's in meters over here, we'll need to rearrange this. We'll need to rearrange this by converting 400 nanometers into meters. And here's a test of your conversion skills. You should be able to understand what the conversion factor is between meters and nanometers just by looking at the prefix. So the prefix nano refers to the number 9. So 400 nanometers is equal to 4.0 times, 400 times 10 to the power of negative 9 meters. Alright? And now, when you do this calculation, it ends up being about 7.5 times 10 to the power of 14 1 over second. Alright, and the unit of frequency over here is 1 over second, and it is also known as hertz. Alright, if you're a musician, you'll know about hertz. It's how you tune your instrument and more. Alright, so now that we have our frequency, we can plug it straight into E equals to hv, right? So E is equal to our Max Planck's constant, which is 6.626 times 10 to the power of negative 34 joules seconds. And are you starting to see how seconds will cancel here, leaving us with just joules? And we multiply it by this the number that we just calculated, which is our frequency, right? 7.5 times, 10 to the power of 14, 1 over seconds, all right? And as we can see, seconds and seconds cancel over here, which leaves us with a number that, if you calculate, is 49.725 times 10 to the power of negative 20 joules. Alright, and we haven't covered significant figures yet, but if you are using the correct amount of significant figures, it should be 5.0 times 10 to the power of negative 19 joules, or something similar. And if you don't want to write out joules every single time, you can just write out J, because that's an abbreviation for joules. Alright, that's it for now, but in the next video, I'll go on and I'll cover more about the Bohr model of the atom. Alright, I'll see you then. Bye-bye.